Okay, this video is for the second part, or the end of the section 5.5 notes. So we did this problem in class. You were kind of left to finish it on your own, but if you didn't get it finished, here is the solution, so you can pause the video and get that filled in your notes. Maybe kind of go back and review trapezoid rule. And then let's look at this one. So this is often how they present things. They give you a table. So in this table we have these temperatures for all of these time periods. So what we're given is discrete temperatures. What I have written here is we're given discrete temperatures. But as you know, temperature is continuous. So, there's temperatures in between these times. So we want to know what is the average temperature. Now, if you pictured, just going to do a tiny little graph over here. If you sketched this, time would be on your x-axis, and I don't know, we'll say Fahrenheit, degrees would be on your y-axis, and you'd have some kind of graph. I don't know what it looks like, but it looks like it goes up and comes down. So say something like that. So they've given us just discrete temperatures. So when we take the area under the curve, which is what we're finding when we do an integral, we're finding this area under the curve. That'll give us our average temperature. And we're going to do it using trapezoids. So first of all, it's a 12-hour period. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, we have 12, not counting the first one. So we have 12 data points. So on this one, our delta x is going to be 1. So you can think of each of these from 1 to 2 as a trapezoid, 2 to 3, 3 to 4, and so on. So our delta x is going to be 1. So our average temp is going to be, and I'm going to do an approximate here because we're going to get a decimal. So our formula says delta x over 2, right? So that would be 1 over 2. Trapezoid formula says delta x. Our delta x is 1 over 2. And then we do f of 0, plain old f of 0, plus 2 times f of 1 plus 2 times f of 2. I'm not going to write all these. Dot, 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 dot. We would do 2 times f of 11. And then the last one would be whatever the temperature is at 12. Okay? So these values are coming right from your table. So your f of 1 is going to be 65. Your f of 2 is going to be 66. Your f of 3 is going to be 68. So this is what it's going to look like. 1/2. F of 0 you can think of as our starting point, 63. And then f of 12 is going to be our ending point here, 55. So we're going to have 63, not multiplied by 2, plus 2 times 65, plus 2 times 66, plus 2 times 68. I'm not going to write all these. I think you get the pattern. Plus, this would be my f of 11, 2 times 58, plus the last one would be the 55, not multiplied by 2. Put all that in your calculator. I got 782. And remember, we're looking for the average temperature over 12 hours. So we want to take that. Obviously, the average temperature isn't 782. That is the area under the curve. So we want to figure out an average temperature over 12 hours would be 65.17. I guess it doesn't tell us what these are, so we'll just put degrees. I don't know if they're Celsius or Fahrenheit. Okay, so that's the average. So this, I think I may have misspoken up here. What the Riemann sum gives us is the area, total area under the curve, And then to find the average, we would divide it by the 12. Okay, let's take a look at one more here. Slide my paper up a little. Okay, so this is the same deal. You're given a table. This is kind of an introduction to sort of where we head with integrals. What they're giving us here is velocity. So it says at time equals 3 seconds, a hot air balloon is 50 feet above the ground. Write an expression involving an integral that gives position. So we're looking for position of the balloon in feet after or at time equals 15 seconds. So this is 0 seconds, this is 15 seconds. Use trapezoidal sum with 3 subintervals. So this means our n is 3. Indicated by the table to approximate the position. So once again, we're looking for position of the balloon at 15 seconds. So we know that when we're given position and we take the first derivative of position, so this is derivative, we get velocity. So if we're given velocity and we take the antiderivative, so think going in reverse. So antideriv, if you're given velocity and you take the antiderivative, it will give you position. So we're going to spend more time talking about this, but start getting in your head, antiderivative is the same as the integral, which is the same as the area under the curve. And when I say under the curve, what I really mean is between the curve and the x-axis. So they're giving us velocity in this table. They're asking us for position, so we want to go in this direction. So we need to find the antiderivative of velocity. Or in this case, we're going to use trapezoids. So we're going to use trapezoid approximation to find the area under the curve. Area under the curve, integral, antiderivative, all the same thing. Alright, so if I were to write this as an integral, I would say, well, I'm starting at 0 and going to 3 time, no. Scratch that. I'm starting at 3 and going to 15. That's my time, or my x, of some function, which is a velocity here, dx. Okay, so this is what I'm approximating, the integral, or the area under the curve, using trapezoid. Alright, so we always need our delta x for trapezoid rule. So that's going to be 15 minus 3, upper bound minus lower bound, divided by 3, because they asked for 3 subintervals. So that gets me 12 over 3, or 4. So delta x is equal to 4. Alright, so our position, I'm going to write position because that's what they asked us for, which is coming from this integral, and we're using trapezoid approximation to find this. It's going to be delta x over 2. So 4 over 2, and we're going to start at 0, and then 2, hang on, 2, geez, times f of 3, plus 2 times f of 8, bleh, plus 2 times f of 12, plus f of 15. So I have this 0 in here, which is actually just going to give me 0. And then f of 3, f of 8, f of 12, f of 15. So I have 2, this is going to be 0. F of 3 is 30. f of 8 is 75. F of 12 is negative 45. I'm going to talk about this negative in a second. And the last one is just not times the 2, but just the 20. Okay, you're going to put all that in your calculator. I got 140. So our approximate is 280. And remember, this is a position or a distance. So this is going to be feet, not feet per second. So we're saying at t equals 15, it's traveled 280 feet. Now the one thing I wanted to mention, which we'll get into more later, but this is a good foreshadowing problem. If you plotted this roughly, if I just plotted those points and attached them with lines, the graph looks something like this. So the area between the graph and the x-axis is this area and this area. And you can see because of this negative, we have some negative area. What happens when you do a Riemann sum is this negative area ends up getting subtracted off. That is also what happens when you do an integral. If you have a function where you have some area that's under the x-axis, these values will be negative. So when you find the area between the curve and the x-axis, these are positive, these are negative. So this area under the x-axis is subtracted off. So the area that you get is just the area above the x-axis. And that's what we have here, because this negative was minused off. Okay, and then the last one was your turn. Remember, when you're doing these, I would say first thing you want to do is put these guys in your calculator. So if you put this in your calculator, I got this as the area from my calculator. And when I did it using trapezoid approximation, I got 1.1169, so pretty close. So I'd like you to try this on your own. Pause the video and try it. And then, which is what you're going to do right now, and then come back and look at this solution and see if you got it right. So try the whole problem. Don't look until you've tried it. You should get this. So if you've done it a couple times and you don't get that, then go ahead and look at this. So here is my work for that problem. So I'm going to end the video here. You can pause this if you want to look at it further. That's it for 5-5.